Just going back to what we have been working with concerning exponential equations. Okay, and we started out with those equations that have a common base, and where we left off, okay, happened to be in the category of exponential equations that do not share a common base. And we have just referencing what we have in the first part of the review handout, and we have among the equations that fall into the latter category. Okay, so we have for numbers 20 and 21, okay, we have the variable x, which we are looking at solving for only on one side of the equation, and we have those affecting the exponential base 5. And for what we have in the case of number 20, okay, so we've got 5 to the x plus 2 is equal to 18. And for what we have here, if you have the variable in exponential position and only on one side of the equation, okay, it can be advantageous, for the lack of a better term, to create the pathway that will lead to the change of base formula. Okay, so we have with 5 to the x plus 2 is equal to 18, and what I mean by changing over to where we can use the change of base formula, I can once again take care of the exponential base 5 and just have the left hand side of the equation at x plus 2. Okay, and to make this possible, I can just take the base 5 logarithm of both sides. Okay, and if I do this, okay, so I have the base 5 logarithm of 5 to the x plus 2 is equal to the base 5 logarithm of 18. Alright, so again, along the line to the base a logarithm of a to the x, again, we had the reduction to what the power was. Okay, in this case, the left hand side, okay, we have transformed to x plus 2. And again, we have equal to the base 5 logarithm of 18. And again, you'll likely not have a base 5 logarithm in your calculator, but you can utilize the change of base formula. And you can use either the ratio of natural logarithms or base 10 logarithms. It does not matter. Okay, and we'll just take the natural logarithm in this case. Right, so you have the natural logarithm of 18, and we have divided by the natural logarithm of 5. And so for what we have in the ratio, and we have in this case, right, so among the first digits, okay, we have 1.7958. And if we look at subtracting 2, and we'll have for x, again, it's said to round to the nearest 3 decimal places. Okay, so for this 1.79 plus number, taking 2 away, okay, we will have for x, we will end up with a negative quantity, which will be to the nearest 3 decimal places at negative 0.204. And once again, we have with number 21, okay, we're still working with the exponential base 5. And for what we have in this one, okay, so this time we have 5 raised to the x minus 1 is equal to 3. And for this one, okay, just as I transform the left hand side to x plus 2, I can do the same thing translating to where the left hand side of the equation is going to be x minus 1. So again, I can take the base 5 logarithm of both sides, So we have the base 5 logarithm of 5 to the x plus 1, x minus 1. So that's going to be x minus 1. Again, we have is equal to the base 5 logarithm of 3. And utilizing the change of base formula, again, you could take the ratio of natural logarithms or base 10 logarithms. And here we'll just take the ratio of base 10 logarithms. Okay, so you have, in this case, we have the base 10 logarithm of 3 divided by the base 10 logarithm of 5. And so we're going to have x minus 1 equal to, and we have from the ratio, okay, we have among the first digits, okay, we have 0.6826. And as we look at isolating x, so we have upon adding 1 to both sides and to the nearest 3 decimal places, okay, we're going to have x to come out to about 1.683. All right, now in the case of what we have in number 22, okay, we're going to have x to appear on both sides. Okay, now we got 4 to the x plus 1 is equal to 18 to the x minus 3, and in this one, okay, so we got 4 and 18 both as exponential bases, and it's really to no advantage to apply the base 4 or the base 18 logarithm. Okay, if I had just the variable on one side, let's say if it were on the left hand side, I could take the base 4 logarithm, or if it had to be on the right hand side, I could take the base 18 logarithm. But trying to do either one, it creates a little bit of static and just makes the problem pathway to arriving at a solution a little bit longer. So we have in this particular setup, okay, so we have with 4 to the x plus 1 equal to 18 raised to the x minus 3. Okay, so if you have the variable exponential expressions on both sides of the equation, okay, you can take either the natural or base 10 logarithm on both sides, and we'll just take the base 10 logarithm again. Okay, so have base 10 logarithm of 4 to the x plus 1 is equal to the base 10 logarithm of 18 to the x minus 3. Okay, notice we don't have any match between logarithmic and exponential bases, and so what we will do here is that with the powers, okay, we're going to make these into binomial coefficients. So for this term, okay, we can say we have all of x plus 1 times the base 10 logarithm of 4 is equal to all of the quantity of x minus 3 times the base 10 logarithm of 18, and for what we have here, okay, so I'm going to remove the parentheses, so we have a couple of base 10 logarithmic terms on the left hand side to be formed. Okay, so we're going to have x times base 10 logarithm of 4 plus the base 10 logarithm of 4 is equal to, and we have x times the base 10 logarithm of 18 minus 3 times the base 10 logarithm of 18. All right. So we have for this set of terms, okay, and we got x terms on both sides of the equation, and I'm going to put these together. Okay. And times, I'll just keep the x terms on the left hand side. So I'm going to keep x times the base 10 logarithm of 4 where it is. So I'll just move the term x times the base 10 logarithm of 18 by subtracting. And what I'll do here, okay, so we have just keeping the non-variable terms on the other side, so I'll just move the base 10 logarithm of 4 by also subtracting. Okay. So for what we have here, we got the difference in the variable terms. So you have x times the base 10 logarithm of 4 minus x times the base 10 logarithm of 18. Okay, and that is going to be equal to, again, negative 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. Okay, and again, we're looking at solving for x, so we've got the x terms on the left, and to get this to a single x term, okay, I can factor out x, and so we're going to have just sort of displaying in factored form. So I have x times the quantity of the base 10 logarithm of 4 minus, okay, the base 10 logarithm of 18, and we have this equal to negative 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4, and looking at isolating x. Okay, so we have a ratio here whereupon we have negative 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4 and we have all over, okay, the base 10 logarithm of 4 minus the base 10 logarithm of 18 and just taking what we have here and putting in, say, for calculator form. Okay, so I want to signify that the difference in the numerator is going to be involved in the division, so just kind of symbolizing. So we'll have grouping symbols with parentheses around negative 3 times, okay, the base 10 logarithm of 18. So you have parentheses around 18. You have minus the base 10 logarithm of 4. And again, to signify that we are dividing by this whole difference. Okay, so we close out with parentheses. I should say, signify that we are dividing into this difference. Okay, and again, we have divided by the base 10 logarithm of 4 minus the base 10 logarithm of 18. So I'm just adding an extra layer of grouping symbols. Okay, so you have divided by the base 10 logarithm of 4 minus, okay, the base 10 logarithm of 18 again, we have closing out, and we have, in the case of x, to about the nearest 3 decimal places, okay, and this will come out to about a 6.687. Okay, now for what we have in the case of the next 2 items, now we have involving the natural logarithmic exponential base e, and we have here, okay, so we have, first of all, we have e to the x plus 1 is equal to 14, And for what we have here, okay, so I can go ahead and just take the matching logarithmic base, which we have in our calculator. So you're looking at the base e logarithm of e to the x plus 1 is equal to the base e logarithm of 14. So left hand side, okay, so I have at x plus 1 and base e logarithm of 14, okay, that's for the other display, okay, that's the natural logarithm of 14. So no change of base is needed on this one since I have the presence of the base e or the natural logarithm function available in the calculator. And so for the natural logarithm of 14, okay, this number can have over 2.63. And looking at solving for x, okay, so if I take 1 away from both sides, and it's going to be for x, okay, to the nearest 3 decimal places, okay, this is going to come out to about 1.639. Now, in the case of number 24, now we got the variable x on both sides of the equation, and we have e to the x minus 2 is equal to 3 raised to the x plus 1. And in this one, now I'll just move down. Again, we have e to the x minus 2, okay, is equal to 3 raised to the x plus 1. Okay. And again, if you had the variable exponential expressions to appear on both sides of the equation, okay, again, you can use either natural or base 10 logarithms. And now you could use either one, but since we already had the presence of e, it might save you at least half a step in terms of arriving to the solution. So we'll take the natural logarithm both sides on this one, but you can still use a base 10 logarithm. And just re-emphasize, okay, so you have the natural logarithm of e to the x minus 2. Again, a natural logarithm will be a base e logarithm. Okay, so the left-hand side translates out to x minus 2. Now for what we have to the right, you don't have a match between the exponential and logarithmic bases, since e is not exactly or not quite 3. So for x plus 1, okay, again, I'm going to make this into a binomial coefficient, kind of like what I did earlier with number 22, okay, where I had moved the x plus 1 to x minus 3. Okay, so we're going to have the quantity of x plus 1 times the natural logarithm of 3, and looking at distributing, okay, so we're going to have x times, okay, the natural logarithm of 3, and we have plus the natural logarithm of 3. Right. So we have a couple of x terms, one in the form of x itself and the other one where we have x times the natural logarithm of 3. And if we look at combining the variable terms and separating from the other non-variable expressions, so I'm going to take x times the natural logarithm of 3 away from both sides, okay, just to have x on the left-hand side, and everything else we'll have over to the right. So I'm just going to add 2. So we're going to have x minus x times the natural logarithm of 3 is equal to the sum of the natural logarithm of 3 and 2. And again, we have on the left hand side we have x as a common factor, and factoring out x. Okay, so I have x times the quantity of 1 minus the natural logarithm of 3 is equal to the natural logarithm of 3 followed by the addition of 2. And for what we have in the case of x, again, we're going to have a ratio. So you have the natural logarithm of 3 followed by the addition of 2 over all of 1 minus the natural logarithm of 3. And just setting things up where I can perform in one calculator operation. So again, clustering together the terms in the numerator. Okay, so I have the quantity, use parentheses. I have the quantity of the natural logarithm of 3 followed by the addition of 2. Can close out for the sum. Again, we have forward slash to indicate division. And again, have divided by all of 1 minus the natural log of 3. And then close out for this difference. And for what we will have in the case of the approximate value of x, okay, and that is going to be about about negative 31.422. So we got here, let's see. Okay, so again about negative 31.422. All right, now in the case of the test for review study questions, okay, and we have in the case of the first item, okay, from this particular set, okay, now we got in this one, so we got for the test for study questions, okay, so we got an exponential equation that shares a common base. Here we have 8 to the x plus 2 is equal to 4 to the 2x. So we have 8 to the x plus 2 is equal to 4 to the 2x. And for what we're going to have here, okay, now, okay, so you have the common base, okay, which is going to be at 2. And now, let me pause right there. Okay, one might be thinking, could you still take the natural or base 10 logarithms both sides and treat x plus 2 and 2x as variable expression coefficients? And the answer to that question is yes. Okay. It would involve more steps, it would be more entailed in terms of getting to x, but if you perform the algebra correctly, you will get to the right result. But acknowledging the common base and writing in terms of that common base, it will save you quite a few steps. Now, for 8 and 4, okay, we have a common base with 2. Okay, so if I write 8 in terms of base 2, now we have 8. It's going to be at 2 to the 3rd and raised to the x plus 2. So you have 2 to the 3rd raised to the x plus 2 is equal to, now we have for 4 is going to be 2 squared, and this will be to the 2x. And looking at the power property, okay, so we have 2 to the 3 times the quantity of x plus 2. And we have equal to 2 raised to the 2 times 2x. And for what we have here, okay, so we've got 2 raised to what is going to be the 3x plus 6 power. And for 2 raised to the 2 times 2x, so this will be 2 raised to the 4x. And now we have single base 2 terms. on both sides, and we can set the powers equal to each other. So we have 3x plus 6 is equal to 4x. And just gathering together the variable terms. So I have 4x by itself, and I can just move the 3x upon subtracting. So we have 6 is equal to x, so we can declare that the solution for x is going to be 6. Okay, now we have in the case of the following group, okay, and we have from the set, and we have for number 4, okay, and again we have just change of base formula situations involved, okay, and we have first of all, okay, we have with the base 3 logarithm of 24, and what I'll do here, just bring this on down. Okay, so you have for number 4, we have the base 3 logarithm of 24. And again, we can utilize the change of base formula. Okay, so let me mention, okay, for the base 3 logarithm of 24. Now, 24 is a multiple of 3, but it is not an integer power of 3. So, for what we have in the case of the base 3 logarithm of 24, I can apply the change of base formula. Again, I can go with ln or log. Okay, so we have the ratio of natural logarithms. So I'm going to have that of 24 over the natural logarithm of 3. And in terms of the reduction, okay, rounded to, again, about the nearest 3 decimal places. And for this output, this will be about a 2.893. Now, for what we have in the case of number 5, okay, and this one could be looked at from different angles. Okay, now we have the base 5 logarithm of e squared notice we have the natural logarithmic exponential base at e, and this is taken to the second power. And here's one approach. Now we can take, okay, look at a is being represented by 5 and m is being represented by all of e to the second. So we could say that we have, and we can apply, let's see, so the base 10 logarithm, since I already have the e present. Okay, so we can say we have the natural logarithm of e squared. We have all over the natural logarithm of 5. And just for, let's say, just for calculator display purposes. Okay, so I got the natural logarithm of e squared. So I got the natural logarithm of e. We have 2 to the second. Divided by, okay, so you have the natural logarithm of 5. And so for what we will have in this case, okay, so this will be about 1.243. Now something that might have appeared before you, okay, is that, okay, we had e to the second power, and among the properties of logarithms we have encountered, okay, was converting from exponent to coefficient, and one might wonder if you could write the 2 as an exponent, and the response is yes. Okay, you could do it that way. So you have like the base 5 logarithm of e to the second. You could write this as 2 times the base 5 logarithm of e, and so you have 2 times, and again you can just apply the change of base formula. We have the natural logarithm of e all over the natural logarithm of 5 had you done it that way, you'll still get to the same result. Still arriving at 1.243. Now, for what we have in the case of number 6, okay, this one, they can still use the change of base formula, but with base 6 logarithm. 216. Now before in number 4, 24 was a multiple of 3, but it was not an integer power of 3. But now in number 6, we have the attachment to be both a multiple and an integer power of the logarithmic base, because 216, not only is it divisible by 6, but it is also an integer power of 6. So if I were to rewrite 216 in terms of base 6, okay, so 216 is going to be 6 to the third. So I'm back to the base a logarithm of a to the x is equal to x property, and in this particular case, all right, that becomes 3. And I'll just mention this case. If I had the base 6 logarithm of 216, had I used change of base formula, whether it's the natural or base 10 logarithm of 216 over the matching base of 6, again it could be ln or log in the numerator and denominator, and the reduction is still going to be the same, where we end up at 3. Alright, now in the case of looking at exponential expressions and going to logarithms, now we have for numbers 7 and 8. Okay, so we got writing as sums and differences of logarithms, and we have for number 7, okay, so we have the base 3 logarithm of x squared times the square root of y plus 4, and we have all over the 4th root of the cube of z plus 2. And in terms of writing, okay, what we have here, okay, so if I were to express the radicals as non-integer exponents, so I'm just going to start out doing a rewrite. Okay, so I have a base 3 logarithm okay, so I have x squared, and for the square root of y plus 4, okay, so we have y plus 4 to the 1/2, and for the 4th root of the cube of z plus 2, so I have the quantity of z plus 2 to the 3/4, and just taking what we have here, okay, so just looking at expanding this expression, okay, so again I have 2 factors in the numerator and 1 in the denominator, and so just initiating the expansion process. Okay, so again, multiplication is going to imply addition, and division is going to imply subtraction once we write the terms in expanded form. Okay, so we have the base 3 logarithm. So if I go with what's at the top first, okay, so I have base 3 logarithm of x squared, and we have plus the base 3 logarithm of the quantity. Okay, we have a y plus 4 to the 1/2. And we have minus, okay, the base 3 logarithm. And we have of the quantity of z plus 2 raised to the 3/4. Okay, and looking at taking what we have and expressing once again the powers as coefficients. Okay, so here we're going to have 2 times, okay, the base 3 logarithm of x, and we have plus, okay, we have 1/2 of the base 3 logarithm of the quantity of y plus 4, and we'll have minus 3/4 of the base 3 logarithm of the quantity of z plus 2. Now it doesn't have to be in this exact order, okay, but again, you're going to have 2 positive logarithmic terms in the variables x and y, and the only negative base 3 logarithmic term is going to be what we have in the variable z. And for what we have in the case of item number 8, okay, and we got for this one, okay, so we have the base 5 logarithm of 7 times t squared u to the 3rd all over v to the 5th times z. Okay, so for what we have here, we got, okay, we don't have any non-integer exponents, and all the coefficients are integers. Okay, so I can start expanding, and so we have 3 factors in the numerator, 2 in the denominator. Okay, and just looking at expressing in expanded form, so just take the top layer first. So we have, first of all, we have the base 5 logarithm of 7. Then we have plus, okay, the base 5 logarithm of t squared. And I have plus the base 5 logarithm of u to the 3rd. And for what I have in the denominator, again, division implies subtraction. So we have minus the base 5 logarithm of v to the 5th. And we have minus, okay, the base 5 logarithm of z. And so just looking at the exponents again, rewriting as coefficients. Okay, so I have this process to affect 3 terms here. Now for the base 5 logarithm of 7 at the front. Okay, now if I leave in exact simplified terms, now 7 is not a multiple of 5, and it is not going to be an integer power of 5. So the exact display, okay, this will stay locked in as such, where we still maintain the base 5 logarithm of 7. And then for the terms that follow, okay, we will have 2 times the base 5 logarithm of t, and we have plus 3 times okay, the base 5 logarithm of u. And we have minus, okay, we have 5 times the base 5 logarithm of v. And we have minus, okay, the base 5 logarithm of z. All right. Now, so this is what we have here. Now, just going back to what we have with exponential equations. Okay, and we have, in the case of number 11, now we got 2 to the x is equal to 3. And this one, I say arguably the quickest way to get to x. Now x is on one side of the equation, so I can directly create a pathway to the change of base formula. Okay, so I can just make the left hand side in terms of x upon taking the base 2 logarithm on both sides. So for the base 2 logarithm of 2 to the x, again you have your reduction on the left hand side to go to x. Again we have x is equal to the base 2 logarithm of 3. And again I can apply the change of base formula where you can either take the ratio of base 10 or natural logarithms. So here I'm going to have the natural logarithm of 3 all over the natural logarithm of 2. And we have, in the case of the ratio here, okay, so this will come out to about 1.585 if you round to the nearest 3 decimal places. Okay, and just kind of going back to the hypothetical question. And I address it if you had a common base to begin with. But could you still apply natural or base 10 logarithms to both sides, regardless of whether you have a common base or not? And again, you can still do that. Say if I took, say, the natural logarithm of both sides, say I have natural logarithm of 2 to the x is equal to the natural logarithm of 3. And if I notice we don't have a match between the exponential and logarithmic bases. So again, for this particular x, I can make this into a variable coefficient, whereupon I'm going to have x times the natural logarithm of 2 is equal to the natural logarithm of 3. And guess what we have with division, so this will come out to natural logarithm of 3 all over the natural logarithm of 2. Same ratio, and you still come out to the same decimal value. Okay. And again, to the nearest 3 places, again you have right at 1.585. Okay. Now, for what we have in the case of number 12, and we have going back to, I think, the natural logarithm base e. Yeah, so you have e to the x minus 2 is equal to 14. Just setting up what we have here. So you have e to the x minus 2 is equal to 14. Okay, see, it's almost like deja vu, but we had a different variable expression to which e was raised earlier. Okay, so I can take, once again, the natural logarithm on both sides. I'm just going to, at the moment, display ln as log with the e subscripted. Okay, so left hand side we'll have x minus 2 is going to be equal to the natural logarithm of 14. In fact, you could have gone ahead and written this as ln of 14. And for the natural logarithm of 14, okay, again, had that 2.639 number. And getting x by itself. So if I add 2 to both sides, and so here we're going to have the x is going to be at 4.639 if I take to the nearest 3 decimal places. Alright, now where there's going to be quite a bit of number crunching done in comparison, and we have for number 13, okay, so we have 10 to the 3x plus 1 is equal to 12 to the x minus 1. Again, we have the exponential expressions to be an x, and we have to appear on both sides, and you can still either use natural or base 10 logarithms. And since I have the exponential base 10 at least on one side, it'll save you probably at least half a step in terms of getting to the solution for x. Okay, so we'll just take log on both sides. Okay, so we have on the left, okay, log is going to be a base 10 logarithm, and base 10 log of 10 to the 3x plus 1. Again, this will go to 3x plus 1. On the right, I don't have such a match, but with the x minus 1, I can make this into a binomial coefficient. So going from exponential to coefficient position. So I'm going to have all of x minus 1 to multiply the base 10 logarithm of 12. And looking into what we have in expanded notation, okay, so we have 3x plus 1 is equal to x times, okay, the base 10 logarithm of 12. And we have minus, okay, the base 10 logarithm of 12. And looking at putting our x terms together, and we have the consolidation on the left. Now we just have everything else on the right. So I just move the 1 over by subtracting. Okay, so for what we have in this arrangement, okay, so we have 3x minus x times the base 10 logarithm of 12, and we have is equal to the negative of the base 10 logarithm of 12 followed by the subtraction of 1. And looking at what we have here, again, we're solving for x. So factoring, okay, so I have x times the quantity. Okay, we have a 3 minus the base 10 logarithm of 12 is equal to the negative the base 10 logarithm of 12 followed by the subtraction of 1. Okay, and so just isolating x. So this will be equal to what is going to result from taking the quotient of negative base 10 logarithm of 12 minus 1 divided by 3 minus the base 10 logarithm of 12 and for what we have here. Okay, so again, I'm involving more than one term in both the numerator and denominator. Okay, we have activity going on between the terms in both the upper and lower portions of the ratio. Okay, so this signals that if I were to put everything into a single combined expression, say in the calculator, so I want parentheses around both the numerator and denominator terms. Okay, so I have the negative of the base 10 logarithm of 12 minus 1. We can close out for this set of terms, and we have divided by, and we have the quantity of 3 minus, okay, the base 10 logarithm of 12 okay. So for what we have here, so got again the negative of the base 10 logarithm of 12 minus 1, we have divided by, again, all of 3 minus the base 10 logarithm of 12. Okay, so to the nearest 3 decimal places, and we have the x will be about negative 1.082. So we have another case of where you have exponential equation that does not share a common base. Okay. Now, so again, we've dealt with exponential equations, again, some with a common base, others without. And both types, you do have the capacity to use natural or base 10 logarithms on both sides. Now, in the case of the next category of equations, and we have with involving logarithms. And let me just mention, okay, it's a little bit of a backdrop. Now we have dealt with time and again the base a logarithm of a to the x is equal to x. And when we first looked into the properties of logarithms, okay, I said that there was in fact, it was the one that immediately followed this. I think I mentioned that it would probably be a while before you saw this again. And again, you have with the match between the logarithmic and exponential bases. You have for this counterpart here, you have a to the base a logarithm of x is equal to x. Now from the get-go, we've had this property to be used quite a bit for exponential equations. And for this property, this is going to enter the scene quite a bit in terms of logarithmic equations. And again, we still have our other properties. Okay, we have the base a logarithm of m to the r, and again, writing the coefficient originating where it originates from the exponent. So you have base a logarithm of m to the r is equal to r times the base a logarithm of m. And also when we started looking into logarithms, when we had them to originate from taking the inverse of exponential functions, again we had that y is equal to the base a logarithm of x. And again, the characteristics were that a had to be positive with the exception of 1, and that for the attachment that had to be a positive value. So you just have these items in reference or equipment among the tools for what we'll have in the case of solving logarithmic equations. Okay, and in the case of logarithmic equations, okay, and just kind of start off with, say, looking at solving for x, and we'll say we have a couple of logarithmic expressions that will have the same base. And we'll say, for instance, okay, so I got, say for starters, okay, we'll have, let's say, the base 2 logarithm of the quantity of 2x plus 3 is equal to, and we'll say we have the base 2 logarithm of the quantity of x plus 14. Okay, so I got the same logarithmic base terms, and let me mention something here. We had, again, these terms are along the lines of base a logarithm of x, where the base a is going to be at 2, and in both of these you have x at 2x plus 3 as well as x plus 14, and whatever the attachment is must be positive. So I'm just going to go ahead and write this. Okay, so you have from the start, okay, 2x plus 3 must be positive. And also in the case of the attachments, x plus 14, this must also be positive. Okay. All right. Now we got single logarithmic terms in the same logarithmic base. Okay, and this is kind of like sort of an inverse counterpart, where we had single terms in the same exponential base and the terms are raised to powers. So you can go ahead and set the powers equal to each other. Now in this instance, we can just set the attachments equal to each other. So we have 2x plus 3 is equal to x plus 14 and if we look at combining the variable terms, okay, so you have taking x away from both sides, and so we're going to have x plus 3 is equal to 14, and in this case, right, so x is going to be at 11, and you can sort of double check here. 2 times 11 is 22, plus 3 is 25, and 11 plus 14 is 25. So both of these results are positive, and they must also equal each other, and 25 is indeed equal to 25. So 11 does qualify as the solution. And let's say that if we have another instance, okay, and we'll say that we have a base 3 logarithm, and we have of the quantity of x squared plus 3x is equal to the base 3 logarithm of 18 okay, so you have only one expression in x between the attachments. Okay, so just once again, whatever we have for x squared plus 3x must be positive. Okay, and so we have, again, single terms in the same logarithmic base, and I can thus set the attachments equal to each other. Okay, so we have x squared plus 3x is equal to 18, and here I have a quadratic equation, and if I set this up and express in standard form, so we have x squared plus 3x minus 18 is equal to 0. And for x squared, okay, so I have x and x. And then for negative 18, okay, factors whose sum or difference will be on the plus side at 3. So you have more weight given to the addition than to the subtraction. Okay. And so we'll have x plus 6 times the quantity of x minus 3 is equal to 0. Okay, so for the first apparent solution, if x plus 6 is equal to 0, I'm going to have that x is equal to negative 6. And if x minus 3 is equal to 0, we're going to have that x is equal to 3. Okay, and just looking at what we have for the values of x. Okay, so now for the square of negative 6 squared is going to be a positive 36. 3 times negative 6, okay, is negative 18. Now, you have 36 minus 18 becomes positive 18. So negative 6 qualifies. And for 3 squared is 9. 3 times 3 is 9. 9 plus 9 is 18. So the input values of x with negative 6 and 3, those come out to 18, which comes or results as a positive number. So whenever I'm talking about like x, I'm talking about not the variable x per se, but just whatever the attachment happens to be. And so in this equation, okay, we have two solutions with negative 6 and 3. All right, now, so these two examples, okay, we have the appearance of logarithmic terms on both sides. But let's say if I'm looking at just an equation where we have only one logarithm to appear, and let's say that just for starters, okay, if I have that the base 2 logarithm of x is equal to 4. So I got the base 2 logarithm of x is equal to 4. Okay, now I'm just going to stress these items here. Okay, again, you have whatever we have for x must be positive. So x must be positive, okay. And then we have with this other property, so I said this would ultimately enter the scene. So you have a to the base a logarithm of x is equal to x. I'm just going to write this again. So you have the base 2 logarithm of x is equal to 4. And I want to say, if I want to write the left-hand side of the equation as x, okay, what I'm going to do here, notice you have base a log of x is an exponent. And guess what? If I make this into an exponent, well, the exponential base is going to be at 2. So for this equation, I have two sides involved, not just the base 2 logarithm of x, but also the number 4. So what am I going to do here? I'm going to treat both sides as powers to which the exponential base 2 will be raised. Okay, so the equation I have converting as powers on both sides to which 2 is raised. So we have 2 to the base 2 logarithm of x. That will go to x. And so that x is equal to. And now for 2 to the 4th, 2 to the 4th power, you have 2 times 2 is 4, times 2 is 8. And 8 times 2 comes out to 16. And 16 is a positive value. And that will be the solution for that particular equation. Now let's say that if we have, again, as a single logarithmic term, and if I have, let's say, the base 3 logarithm of the quantity of x plus 5 is equal to 4, again, we have with the attachment, okay, x plus 5, again, that must be positive for whatever we have for x. And again, we have the base 3 logarithm of the quantity of x plus 5, okay, as the logarithmic term. And again, we have this term equal to 4. And now we have for the attachment, if I free this up and just get rid of the base 3 logarithmic portion, again, I had this property to utilize. And this time, if I treat both sides as powers to which the base is going to be raised, okay, and this time the exponential base is going to be at 3. So I have 3 to the base 3 logarithm of the quantity of x plus 5 is equal to 3 to the 4th. So the left-hand side, so the exponential and logarithmic bases cancel each other. And so we're going to have the x plus 5 is equal to 3 to the 4th, which is 81. And for x plus 5 equal to 81, it turns out that x is equal to 76. And so going back, 76 plus 5 is 81. That is a positive value. And if you notice, we have 81, the sum, is going to be both a multiple and an integer power of 3, where 81 is like 3 to the 4th, and base 3 logarithm of 3 to the 4th is equal to 4. Okay, so there's a bit of a cyclical pattern if you look into checking the results. And now, say that for what we have as cases here, yeah, let me kind of throw this in. I didn't do it with the other groups, but I'm going to do it with this one. Just kind of throwing in where you might have sums and differences of logarithms involved. Okay, so you got these properties. Okay, so you got multiplication implies addition and vice versa. And again, you have interchange, say, between division and subtraction. Okay, and let's say that if we have something like, so we have for this example, okay, I'll just kind of take what we have here, okay, and we'll say that we have in the layout, okay, so we've got, let's see. Let's say we have a base 4 logarithm of x. And say we have plus base 4 logarithm. And we'll say we have of x minus 6. Is equal to 2. Okay. Again, this might seem like a little bit of a broken record. I just want to mention, okay, so we have with the attachments for x and x minus 6. Oops, my bad. Trying to do a shortcut here. Okay, so both x and x minus 6, okay, they must be positive. Okay, notice you have a couple of base 4 logarithmic terms on both sides. Okay, so if I make this into a single base 4 logarithmic term, so we got addition is going to imply multiplication. So if I squeeze together these terms into one, so we have the base 4 logarithm, okay, and you have of the quantity, okay, so we have x times the quantity of x minus 6, and we have is equal to 2. Okay, so and I can just go ahead and distribute, so I have the base 4 logarithm of x squared minus 6x is equal to 2, and then again, okay, to get rid of the presence of base 4 logarithm, again I can apply, okay, this property again. So this time we're going to have the exponential base to be at 4. So you have 4 to the base 4 logarithm of x squared minus 6x is equal to 4 squared. So left hand side we're going to have x squared minus 6x, and we have 4 squared is going to be at 16. And if I make what I have here into a quadratic equation in standard form, so we're going to have x squared minus 6x minus 16 is equal to 0. And we have looking at factoring. Okay, so I have the quantity of x minus 8 times the quantity of x plus 2 is equal to 0. And for what we have in following through, and we have using the zero product property. So if x minus 8 is equal to 0, then we have that x is equal to 8. And if we have that x plus 2 is equal to 0, okay, so we have that x is equal to negative 2. So we got two apparent solutions. But again, okay, just taking what we have again for the restrictions, especially from this item here where the attachment of the logarithmic term must be positive. Guess what? With x at 8, okay, 8 is positive, 8 minus 6 is 2, also positive, so that checks out. But with negative 2, guess what? With x at negative 2, that has already struck out. And so there were two apparent solutions, but with the restriction that both x and x minus 6 must be positive, negative 2 does not fit the bill, and so there's going to be only one solution for x, and that is going to be at 8.